Okay, good afternoon, everyone. Today we will begin our journey into electronics, electronic devices. We'll begin with diodes first, semiconductor diodes, and then move on to transistors, op amps, and logic circuits. Okay, so key differences between circuit analysis and electronic circuit analysis. Let's see, last notebook, page 1 right here. So far, we have, in 201, you looked at linear circuit elements such as resistors, capacitors, inductors, right? And those were all, so resistors, capacitors, inductors are linear elements. And they are known as linear because the voltage and current have a linear relationship. If you increase or decrease the voltage, the current or voltage for that device increases or decreases proportionally, and vice versa, right? So the reason they're called linear is because voltage versus current has a linear relationship. In electronics, we look at devices that have non-linear relationships in their voltages and currents. Hence the term non-linear devices. Okay, so diodes, transistors, semiconductor devices basically are all non-linear. The voltage and current do not have or do not share a linear relationship. If the voltage increases, it's not a given that the current would also increase. Now, circuit analysis of linear components is analytical. Okay, when I say analytical, meaning there are specific equations, you apply those equations, you plug in the values, and you get an exact answer. Ohm's law, for instance, V equals IR. Okay, voltage is equal to the product of current and resistance. If you know the voltage applied across a resistor, you plug in those numbers, and you can get exact values of current. However, for electronic devices, the analysis is more numerical. So it's numerical methods that we will use. So for circuit elements or circuit analysis, we use analytical methods. And for electronic devices or electronic analysis, wonder how I forgot that. That's another professor calling me, by the way. Oh, I know why it turned off. I didn't mute it. Should have been mute. There you go. Sorry about that. Let's see. Okay, electronic devices are numerical analysis. So the solution is not always exact. Okay, it is approximate. And the reason it is approximate is because we need to use numerous models to describe our devices. Okay, so it's not always exact. Approximate. Now I can make an analogy with a real life scenario. You may have gone for an interview somewhere in your past, maybe for an internship, maybe for a full-time position. And the interviewer, maybe an HR or technical manager, might sit across the table and says, "Tell me about yourself." Anyone ever face such a scenario, right? So all true scenario, always they will ask you, "Tell me about yourself." You should always be prepared to answer that question. If you go online and do some searches, there'll be tips and pointers on how you should frame it, how you should frame your answer, and what you should talk about. Because that is your moment to talk about the qualitative things about you that do not appear on a resume. Okay, so you should always be prepared to describe yourself in like 5 sentences or less. Okay, so if I give you 5 sentences, I would say, describe yourself in 5 sentences. You may be able to do that very easily. If I say, describe yourself in 10 words, you would still be able to do that, right? Some adjectives in there, 10 words. But if I say, describe yourself in 5 words, it gets a little bit harder. If I say, describe yourself in 2 words, or describe yourself in 1 word, as I posted in the discussion forum, then you have to think about it. But no matter what your answer is, no matter what the question is, sorry, whether it's 1 word or 2 words or 5 words or 5 sentences, all of those would describe you, right? Not always the most accurately, but it would still be true, right? So depending on the use case scenario, you could use 1 word to describe yourself, 5 words or 5 sentences. And an analogy can be made to electronic devices. Each electronic device that we'll study in this class can be described using several different models. All of those models are different, but they are still true. Depending on our use case scenario, we can pick and choose which model we want to use. Diodes and transistors, for instance, we can use, well, just diodes, for instance, we can use an on-off state of a diode to perform a quick and easy analysis. Okay, it will give us values of voltages and currents in the diodes and in the circuit. So it is true, but it will not always be accurate enough to describe all circuit conditions. Okay, and you will see as we go along what I mean. There are other techniques. There are about 4 or 5 common techniques that we can use to describe diodes. Okay, all of them are true. The reason we need multiple models is because all electronic devices do not behave exactly the same way under different conditions. Primary variations occur due to temperature, due to pressure, due to environmental conditions. Okay, if you are sending a electronic component in the hot desert where it's more than 120 degrees, your devices may or may not work. If it gets really, really cold, really freezing cold, your devices might freeze up and not work. Okay, there are many reasons, physical, laws of nature, laws of physics, due to which our devices will not work. Something as basic as Ohm's law, we just take it as granted that it works, right? But even that is not true when you talk about extreme environmental conditions. So it will not be true when the temperatures are really, really high or very, very low, whether you're operating in a vacuum, in outer space. So all of those are very different. Anyway, the point being that numerical approaches are approximate answers, and they will all still be true. So as engineers, as working professional engineers, it would be up to you on how to use these models to describe those devices, depending on the circuit conditions and the applications. Okay. All right. So let's take diodes first. Where did diodes come from? The name diode actually comes from, and this I attribute, I will explain. The name diode comes from the fact that the first vacuum tube comprised of 2 electrodes. Okay, and that is where the name comes from. So the first electronic device was a vacuum tube, which had 2 electrodes. It's diode. And when they created a solid state version of the same device, the nomenclature carried over, and they stuck with it and called it a diode. Distinguishing is that it's a vacuum tube diode and a solid state diode. Nowadays, in this modern era, all we work with is solid state devices, and so we simply refer to them as diodes. We don't quantify it by saying it's a semiconductor diode or a solid state diode. Okay. And then, of course, we go into BJTs, transistors, bipolar junction transistors, field effect transistors, and then operational amplifiers, which are built on transistors, and then digital logic systems. Okay. So hit the ground running we shall. Colleague of mine, Professor Chuck Bland, you may have seen him around the department. Um, he is fond of using memes. I am fond of using memes. And he had several excellent ones that he used for 321. So I borrowed it from him. So the reference is that we studied 201. We are not quite done with it yet because all analysis techniques are based on the same three principles, same three equations. You have Ohm's law, you have KCL, and you have KVL. Okay, your entire 201 course is just based on these three equations. That's it. All analysis techniques are derived from these three equations. So you have Ohm's law, you have KCL, and you have KVL. These are the only three techniques that you need to know. Not techniques, sorry. These are the only three equations, the only three principles that you need to be familiar with. The entire circuit analysis, circuit course is derived from these three equations. Your node voltage methods, mesh current methods, power equations, everything is based on, excuse me, is based on these three equations, okay? So when we move from circuit analysis to circuit analysis of electronic devices, we'll have different models. But once we have those models, the circuit analysis techniques remain exactly the same as those in 201. Hence, we are not quite done with it yet. Okay. So the first half of the class, first half of this course, actually more than 50%, about 60%, I would say, we would still use circuit analysis techniques. Now, I'm not going to ask you to draw phasors in here, so you don't have to worry about that. Okay, vacuum tube. So I talked about the earliest vacuum tube, or the first one, was a diode with two electrodes. It's comprised of a cathode and an anode and a heater. You provide energy supply to this heater, heats a filament. The cathode is sitting in close proximity to that heater. And because of the amount of energy that is being transferred from the heater to the cathode filament will emit some electrons. Electrons will float or hover over the surface of the cathode. And then researchers discovered, well, not discovered, but electrons have negative charge. So if you have particles, charged particles floating above the surface of an element, you can place another element far away and if you apply a positive charge to that element, what do you think is going to happen? Electrons with negative charge and positive charge on that plate far away, what happens? It's pulled, attracted, right? Negative charges attract, like charges repel. So the electrons are attracted by the positive charged plate at the anode. Electrons start flowing in this direction. Electrons are flowing in this direction from right to left, right, as the circuit shows. Which direction is the current flowing? Up or down? With respect to the source, with respect to this source. Is it going up or is it going down? It's actually both directions, but we stick with the convention that we use for this education. There is something known as electron flow and something that is known as hole flow. Okay, what we do is we always take current as flowing in the opposite direction of the flow of electrons, right? And so if it's opposite to the flow of electrons, For the energy source, it's going up. And if you think back to chapter 1 of EE 201, a power supply is supplying energy. If an element is supplying energy, current for that source, current for that element is always going from polarity minus to plus. So current should always be flowing from minus to plus. For all other elements that are absorbing or receiving the energy, current will always go from plus to minus. So current flow would go from plus to minus. So for resistors, capacitors, inductors, everything goes from high to low, plus to minus. Everything goes from high to low. Temperature, water flow, fluid flow, everything goes from high to low, right? So current flow for all components also goes from high to low, from plus to minus, except for a source which is supplying energy. And so that is verified right here. All right, let's take a pause, think over that. Let me know if you have any questions. Make sense so far? Okay. All right, so now the electrons are flowing in there. Sometimes it's haphazard. Some of them might bounce off the glass tube, insides of the glass tube. And so the current flow needs to be controlled. The electron flow needs to be controlled inside the tube. So some researchers decided to stick a third electrode in there, kind of like wrapping around the tube between the anode and the cathode, like a cylinder. Okay, so that would be a third electrode. Now you have 3 electrodes in there. The triode. And for more other purposes, better control, better efficiency, they inserted more and more and more electrodes in there. So they started with 2, then 3, 4, 5, 6, 7, 8. I think I've read about vacuum tubes that have up to 12 or 13 electrodes. I've never seen one in person. I've seen vacuum tubes in person, but I've never seen one with more than 6 or 7 electrodes, but I've read about them. Anyway, so you have diode, triode, quadrode, pentode, hexode, so on and so forth. Okay. So that is the diode. All right. So then came the invention of the solid state device. Now, the invention of the solid state device was first pointed out in the late 1940s. There were 3 researchers working at Bell Labs: Bardeen, Brattain, and Shockley. William Shockley, Walter Brattain, and John Bardeen. And they are credited with the invention of the first working prototype of a solid state transistor. It was a germanium transistor. So the names, I'll write them out here. It's a little bit of history. Actually, you know what? Let's go to the previous slide. That's a better place rather than this one. So solid state electronic device. Was a germanium point contact transistor. And you can search the internet. There's famous images that are associated with these. There's 3 gentlemen who are overseeing some lab equipment. And those 3 people are Bardeen, John Bardeen, Walter Brattain, and William Shockley. Okay. Should be K-L-E-Y, Shockley. And they created or displayed a working prototype of the first point contact transistor. And then shortly thereafter, the world just exploded. Like, I mean, the semiconductor industry just grew by leaps and bounds. Okay. As happens every so often, high achieving people like these always have big egos. And so they had a falling out shortly after this. I believe it was Shockley who had a problem with the other two. Okay. So I think William Shockley continued with Bell Labs, but Bardeen and Brattain left shortly thereafter. In fact, it got so bad that when their names were submitted for Nobel Prize, um, I think it was Shockley who said he didn't want to share, and so he didn't want to get the Nobel Prize. But they said, okay, if you don't want to come, then you can't be awarded this prize. And so it just made peace. Well, I guess he didn't make peace with it, but he went grudgingly. But he didn't want to go with the other two. He wanted it all to himself. Anyway, they were awarded the Nobel Prize in Physics in, I want to say late 1940s, 50s maybe. I don't know. Can't remember the exact year, but they were awarded with the Nobel Prize in Physics for that. And then a few years later, is the invention of of this working prototype. Everyone else is also doing research at the same time. They were the first ones who demonstrated a working prototype, right? And then the growth just exploded. So shortly, like 10 years later, perhaps, Jack Kilby of Texas Instruments. So this is in 1958. He was a young engineer who was hired by Texas Instruments out of, I believe, UIUC. I'll have to check my references again. But he was a young engineer who was working on a circuit at Texas Instruments. And there were some sort of issues or problems with that circuit. So he had an idea of why not take all of these components and create them in a single block of semiconductor. And that's where the integrated circuit was invented. Okay. So he is credited with the invention of the integrated circuit. Or more commonly known as the IC. Now, an IC, IC is nothing but a PCB, like a printed circuit board. I'm assuming everyone has at least seen one, if not actually worked with one, right? You saw those either green or brown. Okay, used to be brown because it was copper. The tracks were printed off copper, and it's nothing but a bunch of components connected by wires. Except the wires are now just, seem as if they have been printed on, hence the name printed circuit board. Okay, but it's nothing but a collection of wires. It's a circuit taking wires from point A to point B to point C to point D. That's all it is. You have resistors, capacitors, diodes, all kinds of components on a circuit board with a bunch of wires. A microchip or an integrated circuit is the exact same as a PCB, because all you're doing is you're taking that PCB with these components and shrinking it down to the size of a microchip. That's all. That's all an integrated circuit is. You have these tiny components, and tiny components are all the same. Resistors, capacitors, inductors, diodes, transistors, they're all on the same semiconductor block material. And you have wires running all across the place making these connections. That's all it is. But very easy to say, very hard to actually fabricate. Okay, you need specialized facilities and specialized equipment to actually do that. The integrated circuit is also known as a microchip because the original versions were the size of microns, right? Micron is basically, hold on just a second, let me see. I like to, no. Okay. A micro is basically 10 raised to minus 6 meters, very, very small. You take 1 millimeter, divide it into 1,000 parts, you get 1 micro, 10 raised to minus 6. Human hair is about the size of 50 to 75 microns. Very, very small. Okay. So when the first integrated circuits were invented, the feature sizes were measured in microns. Okay. Hence the name microchip, microtechnology, microfabrication. And the name of that company, Micron Technologies, basically Micron. That's where it comes from. And of course, you take 1 micron and you divide it into further 1,000 parts, you get 1 nanometer. And the existing fabrication technologies, the feature sizes have exceeded even that. We are now talking about, approaching the size of atoms. We're reaching like the quantum limit. So quantum computing, quantum mechanics and stuff. So it's insane how far it has grown. A bit more history about this. Jack Kilby was an engineer. Okay. And about 40 years later, 1998, he was awarded the Nobel Prize in Physics. For a long time, the committee would not consider it because it's not a true physics. It doesn't fall under the umbrella of physics. But then the invention of the integrated circuit has such a profound effect on the world at large over the last several decades that believe they were compelled to approve that request. And so in 1998, 40 years after the invention of the integrated circuit, he was awarded with the Nobel Prize. Simultaneously, few months later, there was simultaneous development in many different places. So remember I said they had a falling out and Bardeen, Brattain, and Shockley all went their separate ways. John Bardeen, I believe, can't remember the university. I want to say it was UIUC, but I may be incorrect. And he did research into superconductivity. He became a professor. And he won a second Nobel Prize. There are very few people in the entire history who have won 2. He is one of them. One other famous person who has won 2. Anyone? She was a woman, Marie Curie. And more amazingly, she won in 2 separate fields. She was the first and probably one of only 2 or 3 who have won it in 2 different fields, 2 different scientific fields. So she and her husband both were awarded the prize in chemistry, I believe, first. And then more amazingly, they had started this institute in France, and where their daughter was also one of the scientists. She also won one, and her son-in-law also, I think, won one. So family of high achievers. I don't know. I'm fascinated by history like that. So, all right, coming back to our history here, semiconductors, like just a little bit before I move on. So all these people went their separate ways, and they went on to found many different semiconductor companies. Okay, one of the companies that was founded was Fairchild Semiconductor, and Fairchild Semiconductor had like 8 or 9 people were working in there, and from Fairchild, there were 2 who went on, and I'll give you the names. So Fairchild Semiconductor Technologies. And these 2 left Fairchild Semiconductor, went on to a different company, or who went on to found a different company. Anyone guess what company was that? Noyce and Moore. It was indeed Intel. Robert Noyce, Gordon Moore, and can't remember the third one. Andy Grove. There was one more. I can't remember the third one. I don't know why it escapes me right now. Anyway, they went on to to co-found Intel, Integrated Electronics, Intel, which, like Boeing, was run by engineers for a very long time. Then you got hedge fund managers to come in And well, if you have not, been reading the news recently, it's gotten worse and worse and worse. Anyway, Intel is one of the few companies in the world that designs and manufactures their own chips. Okay. Anybody can design a chip. With the appropriate software, you could sit on a beach and you can do so. But if you want to manufacture your own chips, or your own integrated circuits, it's a very complex operation, requires hundreds of billions of dollars in investments in these factories. Just to start one small factory would take up to 3 years. It's that complex. Each tool or machine that we use runs into tens of millions of dollars. Even in academic environments, machines can run up to $500,000 to $1 million, just one. And you need to have at least like 5 or 10 of those. Then a production environment is very difficult. So all these semiconductor companies that you hear of, like Qualcomm, Apple, all the big ones, NVIDIA, they all design their own chips, but they don't manufacture them. Manufacturing is very, very different. Okay, it's very complex. There's very handful of manufacturers in the world who can do so, primarily now based in Taiwan. TSMC, Taiwan Semiconductor Manufacturing Corporation is the big one. There's MediaTek. There are a few other players in there. So a lot of them are based out of Taiwan. Samsung is another company that actually designs and manufactures some chips of their own. So Samsung Semiconductor is a different corporation and a different enterprise under the umbrella of Samsung Corporation. Okay, they have fabrication foundries here in the US. Global Foundries was part of AMD. AMD, again, was a spin-off of like Fairchild and Intel. And a lot of the people who were working there went on to co-found AMD. AMD took over ATI, Graphics Technologies, and then they spun off their design and their fabrication. So AMD only designs their own chips now, but the fabrication is handled by Global Foundries. They are based in upstate New York. And so that's where the current state of technology is in semiconductors. All right. From history to the present, let's come back to our class. This, again, I have to give credit to Professor Chuck Bland. All right, so far we learned about electricity, flow of electrons, flow of currents through a circuit, resistors, inductors, and capacitors. Resistors oppose the flow of current, which might seem like a bad thing, but without resistors, we cannot build any circuit, because resistors allow us to control the flow of current in a circuit. Okay, without resistors, R is equal to 0, current would be infinite, and you'd have blown circuits every time you flip on the switch. So a conductor is a piece of material that allows the flow of electricity. Okay, a material that allows the flow of electric circuits or electrons is a conductor. So I would classify materials into two primary categories: conductor and insulator. A conductor would allow or permit the flow of electrons or electricity. Insulator would prevent the flow of electrons or electricity. And then there's a third class of materials, which we classify as semiconductors or semiconductors. Semiconductors will only permit the flow of electrons under certain conditions. These conditions are, of course, based on our application. Differences between a conductor and an insulator and a semiconductor are basically the available electrons for electricity or conduction of electricity. Okay, so in a conductor, material like some sort of metal has a lot of free electrons in its structure. Its atomic structure has a lot of free electrons that are available to move or conduct electricity. So if you supply energy, if you apply a voltage, the electrons will move in response to that external stimulus. Those free electrons are loosely bound to the atom. They're free to move about in the material. Okay. We won't go too much into the device physics of things. We don't even do that for the E major classes. So here I'm trying to find the fine line between going too deep into the physics while still trying to make sense. So we have the atomic structure of, let's say, metallic materials. There's a lot of free electrons. They have enough energy to conduct, meaning to move around. And when the electrons move in a material, we say current is flowing. Energy is being transferred and current is flowing in a circuit. So a conductor has free charge carriers. In this case, they are electrons. The charge carriers are electrons. The electrons are carrying negative charge. They are loosely bound in the atomic structure. They don't need much energy to break their bonds and flow in the circuit. Insulators, on the other hand, have very low, I would say almost no free carriers or very low amount of free carriers. When we use the word free here, it means whether they are free to move, free to conduct. Semiconductors are somewhere in the middle. Semiconductors are elements on the periodic table that have 4 electrons in their outermost valence shell. So again, we won't go too much deep into the physics and chemistry, but I'm assuming everybody is familiar with the atomic structure and with the valence shell, which is the outermost shell of an atom, right? So there are 4 electrons in their outermost shell. To create a stable shell, how many electrons would you need? 8. You need 8 electrons in the outermost shell. And so if you introduce external elements into the atomic structure of a semiconductor, you can now create more free charge carriers than are originally present in that semiconductor. The semiconductor has some free charge carriers, but not enough to be considered as a conductor. So it has more than an insulator, but not quite as much as a conductor. Hence, semiconductor. Okay. So semiconductor has more charge carriers than insulators, but less than conductors. By the way, if you can't read my chicken scratch, just let me know. Sometimes I'm in a rush and I just scribble along. So let's write that again. Insulators and conductors. So the way to make semiconductors into a conductor is by introducing more charge carriers. And that is the process of creating a creating a solid state device based on semiconductors. The whole point is that we should create a device which will allow passage of electricity, right? But we want to be able to control the flow of electrons. And we do that by the introduction of external impurities. So one of the classification that we use for describing whether a material is a conductor or an insulator or a semiconductor is a material property known as resistivity. Resistivity is a material property, and you can see here some of the common resistivity values sorry, right here at the top. 10 raised to minus 6, 10 raised to minus 7, 10 raised to minus 8. All of these are excellent conductors. Have you ever heard of gold tip bonds or gold tip connectors? Right. One of the reasons why we use it is because it's an excellent conductor of electricity, and it's pretty much resilient to environmental conditions. Okay, so it's not just, I mean, people might use it for show, but that's not the reason why I would use it for electronic devices. I actually don't have it with me today, but I have like CPUs, like the actual processors that go into your laptops and your desktops. And if we look at the back side, what you would see is contact pads. There'll be hundreds of contact pads on the backside of the chip, and all of those would be gold. So inside every device that we use nowadays, there'll be a ton of gold. It's just very expensive to actually recover all of that material. So we just throw it away. But gold is used heavily in electronic devices to make like contacts. And then at the bottom here are your semiconductors. Okay. Germanium, silicon, and gallium arsenide. They are all semiconductors. Right. So this is one material property that we use to classify materials. The other that we use is, is known as the energy band gap. Now this is going into semiconductor physics, so I'm just going to give a brief overview, not going into too much detail. So if we take an atom, right, and you have electrons, electrons are in fixed orbits, right, at a fixed distance. Each one of those has certain energy levels. If we create a diagram of those energy levels, we get what is known as the energy band gap, energy band diagram. Okay, it's known as the energy band diagram. The theory is that energy exists in these, the energy that exists in these electrons occupy certain levels. Okay? The electrons cannot have energy values that are outside of those levels. And so it creates bands of energy, hence the energy band diagram. So if you have that energy band diagram, at the bottom you have what is known as the valence band, or the valence energy level. At the top you have, or the other end you have conduction. Okay. If an electron possesses or receives enough energy that it can move from the valence to the conduction band, then it's now free to move about. So if an electron is here, it receives enough energy to move up into the conduction band, it can now conduct. And the difference between these bands is known as the energy band gap. Energy band gap. And this is another property, again, without going too deep into the physics, this is another property that allows us to describe the difference between semiconductors and conductors. Okay. The energy band gap is defined in units of electron volts, and it must be small enough that the electron can occupy that state, acquire sufficient energy to jump over and be free to conduct. And the reason I'm pointing this out is because there are many elements in column 4 of the periodic table. What is the most common one? One of the most common ones. Sorry? Carbon? Absolutely. Carbon has 4 electrons in its outermost orbit, but it is not a semiconductor. The reason is the energy band gap for carbon is about 6.3 electron volts, which is far larger than semiconductors like silicon, which is about 1 or 1.2. Okay. So you cannot impart sufficient energy to carbon atoms that the electrons would jump and go into conduction. So resistivity is one classification or one way to define categories. But more importantly, based on laws of physics, the energy band gap is what allows us to create semiconductors out of different materials. Having said that, however, we can combine carbon with other elements to create semiconductors. Okay. Again, that's discussion outside of the realms of this class. I would just state here, silicon energy band gap is about 1.1, 1.12, 1.1 electron volts, put approximate sign on there. Then carbon is in excess of 6. The exact number eludes me at this point, at this time. Okay. So how can we actually create free conductors or free charge carriers in a semiconductor device? But this is how. Keep in mind, energy band gap is all, I explained about that. We can use germanium, we can use silicon, and we can use other compound semiconductors to actually create conductive devices like diodes and transistors and stuff. But going forward, we'll just think in terms of circuit elements. So silicon has, this is the structure or two-dimensional structure layout of a silicon atom, right? You have silicon atom, and it shares 1 electron each with its neighboring atom. So each silicon atom shares 1 electron with its neighboring atom. Thus, all of them benefit, and all of them have a stable atomic structure with 8 electrons in their outermost shell, right? Now, the most common semiconductor is made out of silicon, or semiconductor material is silicon. Okay. Germanium was actually the first working transistor that was created or displayed, but silicon quickly took over. There are many reasons and many considerations. One of the biggest is that is the second most abundant element on this planet. Silicon is found everywhere. It's basically present everywhere, probably in these walls. It's basically sand, extracted from sand. Okay. And when you create oxide from silicon, meaning silicon combines with oxygen, you get silicon dioxide, which is glass. Okay, that's silicon dioxide. We even eat it. If you look at the food that we eat, you look at the ingredients, you will find silicon and silicon dioxide here and there in some of them. Especially, vitamin tablets, you will see silicon dioxide in there somewhere. The silicon dioxide, titanium dioxide, all sorts of ingredients that go into our food, at least the processed food that we eat. Anyway, so silicon is the second most abundant element on this planet. It has excellent electrical and insulating properties. The oxide actually has excellent insulating properties. And so it's very easy to create devices separated by insulating material by using silicon microchips, okay, silicon semiconductor. So when you have a stable silicon structure, you have electrons in there, they all occupy these bonds, and these are known as covalent bonds, right? Covalent bonds. Now, if you take a material, a piece of silicon at absolute zero, Kelvin scale, Okay, 0 Kelvin, which is minus 273 degrees C. Everything is frozen. It's so cold that I can't move. I can't do anything. I mean, basically, if I was silicon, you can't move. You can't do anything. You have no energy, nothing. Everything is frozen solid. Okay. Obviously, none of us can survive at those low temperatures. But as the temperature rises from 0 Kelvin, it goes to 5, 10, 15, 20, 100, 200, 250, 270, 300 Kelvin. As the temperature rises from 0 Kelvin, energy is imparted, and some of the electrons acquire enough thermal energy that they break these covalent bonds at some energy level or at some temperature levels higher than absolute zero. The electrons, wow, I didn't even pay attention to the time. I apologize. Got carried away. All right, let's end class here. We'll pick up here again on Friday. I'm sorry. I usually pay attention to the time. I don't know why I didn't that today. One thing, ignore the due dates that are there on the Canvas page. I need to organize all of them, and most likely I will do those tomorrow or over the weekend. Okay. Right now, the only thing you need to worry about is homework 1. That's it. So homework 0 is like tutorials, but homework 1 is for extra credit. And I believe that should be due either Saturday or Sunday. I'll make it due Sunday. Okay. But it's all based on circuit analysis. And Friday's quiz will also be simple, basically something about circuit analysis. Yes. Yeah. Yeah. So I'll adjust all of those dates.